So we have a surprise. Our speaker, Mathieu Ropert, who's our family right now, decided to help us and prepare his backup and surprise lecture. This lecture is titled ECS and DoD, and what will happen there, I don't know. Let's give our stage to Mathieu with a big applause.
Thank you so much. Wow, this is the second time and it doesn't get less impressive. There's how many, like 25 rows multiplied by how many you are? That's a lot. And that's good because it's a talk about processing data in bulk. And I can already make an observation. There's some fragmentation. I see some gaps in the sequence. This is not optimized. We will talk about it, but I'm getting ahead of myself. This is a talk about ECS, which you may have heard before, and data-oriented design, which I hope you have heard about before, but let's see. Who here has heard about ECS? Can I have a show of hands? That's not really a lot of people for the internet, like I would say less than 10%. Interesting. How many of you have heard about data-oriented design? That's maybe a third, probably less. I'm bad at math. That's good, that's perfect. You'll learn something today. So, I work in the game industry. And in the game industry, we have this conference every year called Game Developer Conference. That's very original, I know. And there's a bingo card you can get if you want. I don't think it actually exists, or if we just a joke we have. But there's this bingo idea that every time you go there, the freebie one that's in the middle of the bingo card is when someone asks, oh, you should use an ECS, that should solve all your problems. Because it doesn't really matter what the talk's about, QA, any programming topic in the game industry. Someone at the end of the talk will raise his hand and say, oh, you should use an ECS that will solve all your problems. Why? Why are we talking about it? What is this even? If we do a Google Trend search real quick, we'll see that it's been talked about for a bit, but it really started to spike sometime around like 2018, which is about the time when the Unity engine, which you may have heard as like the game engine that powers a lot of like indie and mid-sized games, released an ECS system with a very cool demo called the Mega City demo. If you have not looked at it, it's pretty impressive to look at. And I think that's where the spike came up. And then you can see that every spike, it came down. You may say that maybe during COVID, people stopped using Google, but I don't think that's how that works. Maybe the hype died down? Let's find out. I also did a quick geographical search, and for some reason Sweden came up first. I happen to live in Sweden. I know we have game industry there, so maybe that means I'm the most qualified person to ever talk about this. I'm not sure, but you know, I'll let Google validate me on that one. Anyway, hi, I'm Matthew. You may have seen me earlier. I'm the surprise talk. I'm filling in for someone who unfortunately couldn't be here today. I'm a tech lead. I work at Paradox Development Studio. We make those weird map games that you may have heard about. If you heard about, you probably heard about for thousands of hours. If you don't, try and see you in 2,000 hours. Yeah, there is my contact at the bottom if you want to reach me. So this talk, it's about what's ECS. We keep hearing about ECS. What is it? I'm going to show it. We're going to talk about data-oriented design, same thing, what it is. We're going to talk about cache friendliness, which is basically why are those two things existing in the first place? Why do we try to do cache-friendly data structure? And we're going to talk about coupling, or more importantly, decoupling. So, to go back where it started, let's talk about hardware. Let's talk about chips. So this is some random picture of an i7 that I found on the internet. And I want to take a minute to appreciate the CPU design. It doesn't matter if it's Intel or AMD. I am not here to pick sides. It is amazing that when you think about it, your CPU today runs at what, like 4 or 5 gigahertz maybe? If you do the math in your head, and again, I mentioned earlier as a disclaimer, I'm bad at math, but that means about 4 billion cycles per second. And if you assume that it only takes a couple cycles to make an instruction, you can literally achieve billions of arithmetic operations per second. And that's with one core, and most of those CPUs have 20. And I don't think that's the thing that really resonates with us, especially when we watch like the loading screen of some Electron application. I don't want to bash on Electron or any application really. But when my CPU is able to do 5 billion instructions in 1 second on one core, how does anything take time? Like when you think about it, and it's a thing, I mean, I've been in this business for a bit now. But I still get amazed by like, wait, how much more can I actually do in 1 second? It is crazy. Like even, in school, they taught me like, oh, don't use division, don't use square root, like that's very expensive. Well, I mean, it is. Compared to an addition, we will take like barely a cycle, but it's still like 10, 15, 20 cycle. Your CPU can compute a square root in that amount of time. It's a joke to them. Like, again, if it's running at 4 gigahertz, it can do like hundreds of millions of square root per second. That's not your bottleneck. Like, I swear to God, the division in square root are rarely the bottleneck of your program. It might be for some very specific case, don't quote me like out of context, but in most cases, I tell you, this is not your bottleneck. And, you know, we have SIMD now, SSC, MMX, AVX, and their friends, which means you can also do like several of them in one cycle. Like with SIMD, you can do maybe 4, 8 addition in one cycle, and then you multiply by 20 cores. This is absolutely amazing. This is like, CPUs have gone very, very far. But you know what hasn't gone far? RAM. RAM is about as fast as it was 10 or 15 years ago. And there's this thing called physics, which I'm about as good as with math. But it says that, you know, there's speed of light and there's some stuff happening there. But the main important things to remember is that if your CPU, if stuff has to be close to other stuff to go fast, that's the very physical and scientific explanation I can give you. So like, if you have data on the chip, on the actual physical die of your CPU, then it's fine. If it's further away, it's not fine. And I'm not saying further away like, you know, your colleague's computer over the network or your hard drive. No, I'm talking like your stick of RAM is too far away for your CPU to reasonably operate at good speed. Because you can't do a 5 gigahertz like basically round trip between like a CPU and RAM. Even if they're like a couple, like maybe 10 centimeters across, that's just not how physics work. And that's a problem. So if it's not in a register, which is like the small local like storage of value that your CPU have, or the level 1 cache, we'll talk about caches in a bit, you have a problem. Because if it's not in there, to operate at the CPU's actual like clock speed, it has to be loaded first. And what do you do when something you want is not loaded? Well, you wait. And you can wait a lot. So this is to scale. No, this is not. But this is your nice CPU. This is your nice RAM sticks. Fetching from a main memory is about 100 nanoseconds. All right, so that's about 100 cycles if your CPU runs at 1 gigahertz. It usually runs faster, but that's, you know, let's just consider it the same amount of thing. So it's 100 times. If you need 1 cycle to do an integrate add, you need 100 to read that value from the memory, and then if you need to push it back in another memory, like if you do like a star p++, for example, like you have a pointer to something, and you need to plus it, or even if you prefix it, if you do like star plus, increment a pointer, increment the value pointed by something, a pointed integer, a pointed byte, doesn't matter what it is. You do 100 nanoseconds to fetch the value, so 100 cycle, then you do 1 to actually increment it, and then you do another 100 to send it back. So that's 200 for the price of like 1 instruction you actually really want it to do. If you look at data that is stored in the cache, it gets a bit better because basically if it's already loaded in a register from a previous instruction, it's free. If it's in L1 cache, roughly speaking, I'm told it's about 0.5 nanoseconds, which I mean still pretty fast. If it's in L1 cache, in L2 cache, it's about 4 nanoseconds. I did not bother with L3 cache here. I know CPUs have a lot of L3 cache now, but it's still like it starts growing and growing in like very bad rates. And if you go to main memory, this is 100 nanosecond. If we try to normalize this value, assuming that you know the 1 unit is reading something or writing something to L1 cache, it is 200 times faster to access something that you very recently accessed and is still in your cache than fetching it in main memory. And I did not invent this. This was made, I think, first by Mike Acton at CppCon 2016, although I think it might have been inspired by another talk. But I'm going to do some very advanced PowerPoint skill after being inspired this morning by Ewa. Well, no, not whatever. Here's what I'm going to do. I'm going to show you to scale the time it takes to read something from L1 cache and L2 cache in RAM, okay? So we're going to read from L1 cache because the data is not there, but it's in L1 cache. Poof, done. Did you manage to count? Okay, that's your 0.5 nanosecond. I mean, an equivalent that you can vaguely process in your brain, right? See? Done. Okay, let's fetch from L2 cache now. I mean, you had the time to count in your head. You had the time to realize my presentation was moving on. I guess it's still fine. All right, let's fetch from main memory. Oh, almost half. Past the midpoint now. Come on. Come on. You're almost there. You're almost there. There. Got it. Yep. So that's the difference between like eating the cache and missing the cache. So memory access is slow. It's literally orders of magnitude slower than doing arithmetic at this point, like probably 2 orders of magnitude, roughly speaking. You can alleviate most of that with L1 and L2 caches. I mean, your CPU is trying its best to alleviate that. But if your data is not been recently accessed and therefore in the cache, you have a problem. And now the question is like, but how do I assure that my data is in the cache? Because it's not a thing you're going to do implicitly for like an operating system call or whatever. It's a mechanic that happens for you because, again, your CPU founders are really smart and they're really trying to save you from yourself. So here is like, roughly speaking, how that would work, right? Like you have, let's say you have like, it's a bunch of 64 bytes memory cells or arrays in memory. Each square is about 8 bytes. And they have a line number. It doesn't really matter for this. The main important thing is, okay, I need to read this byte here in memory. Well, those 8 bytes. The CPU caches operating lines, and I think most of them now 64 bytes. The CPU will not just load these 8 bytes you requested, because that's really inefficient if you have like 100 nanosecond like round trip time. Instead, what you will try to do is it can't go faster, but it can fetch more in the same time because it's a latency issue, not a throughput issue. So what it will do is it will actually load all 64 bytes in one go. And it's the same amount of time because the problem is this physical distance. It's not the bandwidth. So what it will do is it will fetch all of it for you. Meaning that if you were just iterating through an array and you get the next one, well, it's already there. So the first one takes 100 nanoseconds, but the second one is free, and the one after that is free, and the one after that is free. And since people at Intel are very smart, 25 years ago they realized, wait a minute, I can predict where this is going. I'm going to load the next one because I can tell that you keep doing references, incrementing addresses. So before you even at the end, I will have loaded it for you. There, I doubly saved you from yourself. You're not even going to have to wait when you're at the end of the line. And you know what they even figured out? It also works in reverse. If I go back, ta-da, it will start loading it from me. That's great. But that's as smart as they go. Like, they can predict that if you keep doing plus plus, you're probably going to continue doing that. And they can predict that if you do minus minus, you're probably going to continue doing that. If you do anything smarter, you're on your own. So, again, as long as the cache can predict where you're going, it can predict your memory access, and you're not jumping too far off, there's a high chance that the data you want is already there or has been prefetched behind the back, even if it was not already there, because your CPU is really trying. If you want to take one takeaway as the really simplest thing is linear access good, random access bad. This is the reason why people will tell you use vector, use array, don't use map, don't use list if you want to go fast. Because iterating through a map or a list is or any form of tree really, is way orders of magnitude slower than iterating through a vector, and for that simple reason. It's because series of pointers are basically random places in memory that you keep jumping to. Chances are they're not preloaded in your cache, so every time you hit a pointer, you wait 200 cycles and then you come back. Right, so now that we've figured that out, how do we use the actual physicality of the machine we're programming for as to our advantage, because that's the point, right? We all programmers, and most of the time we don't like things that go slow. We're here to try to take advantage of the hardware, not work against it. And so, basically, starting the 2000s, people have been talking of this data-oriented design, thinking, like, it's great if you have a conceptual model that helps you to think, but if it doesn't help the machine, then it's good that it helps the programmer, but it really doesn't help the performance. And the question is, can we do both? Or can we at least find a trade-off in which it's still intelligible for a human, because there's a reason why we invented OOP, right? Object-oriented programming. It makes sense to say, oh, all those things are conceptually part of the same object. It would be nice if they were all next to each other, even if the CPU will hate me for that. Can we find a trade-off? That's the point. And the idea is, can I architect my data structure and my code so that every time I do like a bulk operation, I make use of the cache. Again, we're talking about bulk. We're not talking about the one case here. So for example, I work in video games. I do simulations of strategy. Like there is like now thousands or maybe millions of like units running through the world, thousands of like factories producing things, etc., etc. That's the case I'm trying to optimize. It's okay. Like an in-game hour has passed. I'm simulating the passage of time. Simulate the production of all those things. Simulate the fighting between all those units. I'm taking for every unit in the world from 0 to n, do this thing. The thing I'm not trying to optimize is the user has selected one unit, show me its stats. That's the one case. I don't really care if it takes me 5 lookups to get the data because it's only one and I have 16 milliseconds to figure that out. That's not a problem. So the idea is we try to model our operation as a series of bulk transform. If you heard about stud transform or any... Stud transform is basically your go-to algorithm in that case. But it's basically things that operate on a range and that range being an array or something similar. And you try to write pure functions. You don't do side effects because side effects usually require reading or writing somewhere else, which means usually accessing data structures that are not in cache, which means problem. I can make an exception for constants, but roughly speaking, the idea is, okay, let's just take, like if I want to do a transform from like moving a bunch of objects from state A to state B, I take an array of my object and I just do a bulk processing on them. So maybe you have heard about the thing about AOS versus SOA. I know SOA used to mean something else back in the 2000s when I was a young web developer. I'm way past that now, but it's not service-oriented architecture. It's struct of arrays. So here's a very simple like game, if you can call it that, or like an idea of a game. So on the left, you have the traditional object-oriented representation of a unit. What's a unit in my game? It's a possession, a velocity, and some hit points. For those of you who have never done 3D, don't worry about it. I also suck at arithmetic and linear algebra, but I can tell that a position is 3 coordinates, x, y, and z, and so that's 3 floats. That's basically it. That's all you need to care about and know. And then a velocity, well, it's, if you remember vaguely the concept of vectors, it's also 3 floats. And to update a position, you just added the new velocity. You had the velocity multiplied by the delta of time, and ta-da! You can tell where you are. I'm sure some of you work in astrophysics or whatever from what I've seen at the conference. I probably sound like a toddler at this point, but this is the rough idea. And then since it's a game, we have hit points, because that's, we need to figure out when a unit dies. That's the 3 things we have, okay? So that's 3 floats, and 1 int. 7 ints, basically. 7 times 4 bytes. Okay, that's not too bad. And so all our units in our game, in the traditional sense, would be a vector of all the units. Assuming you don't do like array of pointers or whatever, which is a thing that I've seen people do. Let's try to be good with ourselves and say, no, I don't have a vector of unique pointers to units or something like that, because that would be all around in memory. No, I just have a vector of units, which is already a good case. I've seen many games where it would be a vector of unique pointers of units, and they're just like, my units are somewhere. If we had a strict of array instead, my units thing would be a structure which would be 3 vectors. One of positions, so vectors of 3 floats, one of velocities, another vector of 3 floats, and one vector of hit points, vector of just 1 int. And all those 3 vectors have the same size. If you don't have the same size, you have a problem. But by construction, we guarantee that they have the same size. It basically, if I do like position of 1 and velocities of 1 and HPs of 1, I get the stats of unit 1. That's roughly would be the idea. Why would we do that? That's not an interesting... How many people think that's weird? Or like you would see that you would raise your hand in a code review. Be honest, it's fine. You can tell me my code looks weird. Are they afraid of... come on, find your courage. The more I wait, the more I see hands. Okay, not that many people. But let's look at the memory layout for a second of my classic OOP version. Okay, so I have a unit. It's 3 times 4, 3 quad words. 3 double words, because word is 2 bytes, don't ask. 3 quad words for position, 3 quad words for velocity, 3 double words for velocity, 1 double word for HP. So 12, and 4 bytes. That's my memory layout. But looks pretty dense. Now, if we array that into like an array, you will have like the first 2 units basically, like I don't have that much space on my slide, but assuming like, you know, it's 1 unit, then the other unit, then the other unit, they just look like subsequentially spaced out in memory. That's just how you go all the way to the last one. Cool. So now I'm gonna write a bunch of like operation that my game has to do to simulate the basic game loop of a thing. If you've never seen a game before, what you do is that you have a infinite loop, and you just take some player input into consideration, you update the simulation, and then you render the result on the screen, and then you continue again. That's basically it. It's a while loop that does those 3 things all the time. Let's not care about user input. Let's assume our thing is just a nice demo and the player can't do anything about it. The only thing we do is that we every turn we update the position of the unit, we simulate some damage, and then we render the result on the screen, and then we try again. And then we try to do that as fast as we can, 100, 200 FPS, whatever the guy doing the benchmark is hoping to get. So we have 3 operations. One is update position, one is take damage, and one is render. Update position obviously takes the position and the velocity and writes to the velocity to the position. So that's basically the data structure that it's been using. The left is read access and the right is write access to give you an idea of the data model. Take damage, well, it takes HP and it outputs HP, or it takes HP and it mutates HP, depending how you want to look at it, depending if you're a functional like purist or if you're okay with mutable references. It's the same idea. Finally, we have render. It takes all 3 and it outputs nothing, because either you render it on the screen or you don't. That's basically it. You go through all the units, X, Y, Z, okay, is it visible by the player, do some math, okay, but then put it on the screen, then done, next one. Cool. So what we're gonna do every time in our game is that we're gonna do a for loop for all the units, we're gonna update all the position, then we're gonna do another for loop for all the units, we're gonna take damage, because that's our game systems running, and then finally for all the units, we render them on the screen. That's a reasonable way to write your game. Now, if we look at every operation one by one, I'll color in gray the bits that they don't actually access when they actually get fed the unit through memory. So update position doesn't look too bad. Out of 7 memory cells of 4 bytes, there's only 1 we don't use. So, you know, I'm losing for every time I'm trying to read memory and fill it in the cache and fetch more data through the bus. I waste 1 in 7 cells. I mean, it's not the best rate I ever seen, but it's, you know what? Maybe if it was just that, I would be okay with just saying, yeah, you know what, this DoD thing, like this. No, I'm gonna keep my code as it is. It's fine. It's good. It's good enough. Now, if we start looking at take damage, we can start having a problem. Because 1 in 7 cells in memory is actually something I care about, and the rest is literally noise. My memory bus is spending most of its time fetching data I don't need. And the rest of the time, since I'm probably gonna start reading it faster than my bus can fetch, because only 1 in 7 cells is what I use, assuming that my operation to take damage doesn't take that much time, by the time I'm at the end of my cache line, it would not have had the time to load the next one, because there's barely enough units in a cache line for that to keep me busy for 100 nanoseconds, which is the time I need to fetch the next row. And so I'm gonna wait. You can exactly see the same thing as if you were doing network processing, basically, okay? It takes you 100 nanoseconds to get the next message from the network. Are you done with your work in 1 nanosecond and can you start processing? Or you're gonna have to wait for it to arrive. And you don't wanna wait, you wanna do as fast as you can. You wanna optimize the throughput, basically. If I try to render, it's still not good, I'm still under 1/2. 3 out of 7 cells are used, and the rest is also garbage that is just being fetched in memory from the reason. You can think about the same thing as if you're reading data on a disk or on memory. You have a 1 giga file on the internet, and you actually use 1 in 7 bytes in it, and you still downloaded 1 gigabyte. Why did you do that? Like if anybody was paying for that bandwidth, he would be like suing you. I was like, what the hell? You seen my bill? Here we don't care about the bill as much as we care about how long it took. And I would rather have to fetch 100 megs than have to fetch a gig. Especially if I'm on my phone, like I am right now, roaming. Cool. So what if we do the opposite? What if we make a position, a velocity, and a hit point vector? Well, that starts looking better, because if I do update position, I'm gonna fetch a vector of position and a vector of velocities. And surprise, surprise, CPUs can actually read 2 arrays parallel, and usually both can be loaded at the same time. They're actually pretty good at that. There's this thing called data associativity for caches, which allow memories that would potentially collide because they have the same modulo address to still be able to be held in the cache at the same time, because obviously the cache is smaller than the old RAM, so at some point you need to evict something out of it to make room for new stuff. And one of the rules is that if they have the same modulo address, the oldest one loses. But again, modern CPUs, I think that at least 3 or 4 things can fetch in the same cache thing. So meaning you can be reading 3 to 4 arrays at the same time and not even see a penalty. And if you have like an i9 13th generation, I think it's 12 or something ridiculous like that. So this is probably going to be fine because the update position is only reading 2 vectors. And I'm only going to fetch exactly what I care about, and that's it. Hit point is probably my favorite. I'm just going to be reading 1 array. I'm going to use literally every byte out of it, and then I'm going to go home. And render, same thing. It's only going to look at the first array. It's going to fetch as much as it needs. Obviously, it's still like 3 times as much data to fetch than hit point, but I need those 3 times more data because I just have more stuff that I need to process. So the idea, if you make data-oriented transform, which are small loops that operate on an array of fields. So instead of having like a function that takes object like a field A, field B, or just an object that contains field A and field B, and then does a thing, and then I call that function in a loop, I make a loop that takes the bulk. The bulk is the case I'm trying to write. So it takes both arrays. I actually don't use arrays, use span. It's just array, but better, because you don't have all the extra things from vector that you don't need. It takes 2 span or n span, depending on how many fields I need to read in effect, and it just does like 4 or 0 to the end of whatever, and that's it. So you minimize the amount of data in cache that you don't actually touch, so you maximize how much usage you make of the memory bus, which is your limiting resources in those cases. And you even get something for free, because if you notice, and I'm going to make a small break to talk about architecture and code architecture for a moment. First of all, arguably you're mixing up concerns, because you notice that some of those fields never appear together. For example, like you have position data, and then you have like velocity data, and then you have HP. Maybe you will have to write a function that makes use of both of them, but most of the functions you write, they don't need all those fields. So you're kind of mixing concerns, and you're also hindering maintainability. And I think it's a thing we've been cautioned against since forever, before I was born, surely. You don't need to mix up concerns that don't need to be mixed up. That's why people tell you, like, no, write 2 functions for those things, because you don't need 1 function to do the same thing. Split your data. It's the same idea. It's like, if you have fields that are never accessed if several fields are never needed by 1 given function, what are they doing in the same class? I know that when you think about OP and when you try to write it down, you think like, but that makes sense, because a unit has HP and has a position and maybe an amount of equipment and blah, blah, blah. Yes, but do you have an actual bulk process that needs all those fields together or not? Because if the only thing you have is like a 1-case display for like serialization, debugging, or whatever, I mean, it's convenient for you when you write a UI, but the UI is not the limiting factor in any game I know. If it is, talk to me. You have a problem in your game. Yeah, and it's an all or nothing thing, right? Because you can't reason about data sharing. So if I have an object that has all those fields, a thing you may have noticed, for example, I'm going to make a small aparté about another talk I made about multithreading. Because here's the thing, right? If I have to write the first function, and I have like for example, the update position and the take damage function, they both take a mutable array of units. So what does threading 101 tell me? I can't run them in parallel, because maybe they'll be accessing the same unit at the same time. I don't know. I can't prove that. I might be able to prove that by recursively looking at every function and proving that actually they never touch the same fields within the same object, so I don't need a mutex. But honestly, unless I delve very deep, and I mean, those systems are very, very dumb. In an actual game, especially like complex simulation like we like to do at my company, but in others, you're going to have to read a lot of code to be able to prove that, don't worry, trust me, those 2 functions, they take a mutable object, the same one, but they're never going to touch the same field, so it's okay to thread them. And then somebody will come and don't know about that and just change 1 function, and then suddenly you have a data race that you didn't even know about. If you use the more data-oriented approach and say, okay, no, my transform take arrays of fields, then you can prove by construction those two functions are hitting different parts of are eating different fields, and they can't access anything else because they don't have access to them. They only have what I give them, and then ergo I can prove that they can run at the same time. So decouple your data. But enough about threading. Threading is just the free bonus you get out of this. But if you go back to the original question, okay, you say, okay, Mathieu, I'm convinced. This sounds really cool. I like your slides or whatever. I'm convinced. Don't just ask me because my slides look cool. I mean, I'm glad if they do, but that's not the point. You're gonna run the benchmark, and that's QuickBench. If you've never heard about it, QuickBench is like Godbolt, but you can actually run Google Benchmark and have nice graphs for people who don't like to locally run QuickBench benchmarks and then make graphs. It's great. It does that for you. You just make a screenshot. Done. That's if I have to do the three operations in a sequence. In both data structures, you can follow the link if it's readable enough, and you'll see the benchmark. I do the same exact thing. I have the same two structure that I described earlier, like the three arrays versus the one array of objects. I think there's 100,000 items in both, and I run the free operation in bulk. And I measure the difference. And you're like, that's what? Not even 20% faster. Maybe 15%? Like, I don't know if I want to rewrite my whole program just because this guy at CodeDive told me that it was good, because 15%, that's a lot to teach my colleagues and then rewrite the application. I don't know about that. But here's the catch. This is a slideware, right? This is the perfect case. I have free operation, free fields, and that's the only free data I have. That's not a real unit in any real video game, especially if you have a complex video game or any complex business object in your whatever your thing is. If you're in finance, you would be the same thing, right? I could have a rate, a principal, and a currency, and you'd be like, oh, that's all I need. And you're like, oh no, I need a calendar, I need some payments, blah, blah, blah. And so what's gonna happen instead? Well, you're gonna have a lot of bytes at the bottom that are other fields that people put in the unit too, because they think, the unit can also have that. So let's make a simple thing. I'm not going to implement a billion fields that make sense for a unit. Instead, I'm just going to have an array of cars, bytes, and I'm just going to pad it with more and more data and see how we go. So let's start with padding it with 32 extra bytes. So there's like 4 floats that I have added at the bottom of my struct that I don't use in any of my updates. And I don't change the code. I just pad more and more. It starts getting like 50% faster, something like that, probably more. All right, let's double it. Let's add 64 bytes of padding. Oh no, that starts to say. Let's add 128 bytes of padding at the bottom of my struct and just access the first 3 fields in every update. You start seeing the problem, right? I have good news and bad news. The good news is that there's a bound. There's a bound because at some point it doesn't matter for every object you read, you're hitting the main memory every time you loop. So it doesn't matter if you add even more fields later. You're just gonna your object doesn't even fit in the cache anymore. Any cache L1, L2, L3. None of your object fits in one cache line. So it doesn't really matter how much more data you add to it. At this point, you're already paying the worst cost possible. That's not an argument for doing it, by the way. That's an argument that should scare you and be like, I'm like your profiler is gonna tell you you're memory bound and not like little memory bound. It's gonna be like, oh fuck yeah, you're memory bound. So this is where it stops. Yeah, the bad news is you probably have a bunch of code like that in your application, because I have a lot, and I've been wondering how to improve that. So that's where we come to ECS, because we've been talking for like 30 minutes and we haven't talked about ECS yet, because that was a trick. What is ECS, or Entity Component System? It's a nomenclature and a bunch of frameworks that some people have tried in the game industry for the past, 8 years, 10 years maybe. I think you can find literature all the way to the 2000, but it's really picked up in the last couple of years. So the idea is that, okay, each bundle of fields is called a component. For example, my velocities are a component, my positions are a component, my HP are a component. Then every object in the world has an entity ID. So all my units are entities and they all have an ID from 0 to n, or whatever other key you want. And then each entity can optionally have an arbitrary number of components. So it's what I've done, but on top of that, we introduce optionality. Not every unit has every component. Technically, you can have any combination of component you want, at least in literature, in principle. In practice, we'll see that it's not as good. And the idea is that components can be added or removed. A classic is, If a unit is controlled by a player, it probably doesn't need AI data because a player controls it, so it doesn't need any extra data. But if an AI takes over that unit, then maybe it needs some extra data for the AI state to be saved so it can figure out what the heck it was supposed to do. And what is a system? The S in ECS. It's a transform that operates on a selection of components. And so basically, every time you want to do a global update of your system, you go for every system you have, you gather all the entities that have all the components that this system needs. You basically do a select that returns you like views, zip views if you want, and you feed that to the system. It does a for loop or every of those. And then you continue for the next one by doing the transform in bulk. And then the more fancy your ECS system is, the more likely you will be able to try to say, hey, those two systems don't share any fields, so I could multi-thread them and run them on 2 different cores or something like that. So if I go back to my system, the transform or update position, take damage, and render. This is basically what makes an entity or a possible entity, which is, for example, a unit is an entity that has 3 components. Each one of those is a component, and those are my transforms. That's the idea behind ECS. So the efficiency comes both from breaking objects into components and also from the fact that behind the scenes, we store them into dense arrays, so we maximize cache usage. Now, I could talk about how we implement this, but we only have 10 more minutes, so I'm gonna more like talk like, okay, that sounds like a good idea. I've heard people use them. In practice, does that work? So, the thing it's supposed to give you, in theory, as a framework, is that you have extremely fast and ordered iteration for one given component. Like, iterate through all the position, iterate through all the HP, iterate through all the entities that have this component. It's probably the fastest you can get, because the point is that it's going to try to keep all those in dense linear arrays, and this is the fastest data structure that you can have on a modern CPU, is a dense linear array with no gaps in it. So that's why I was talking earlier about this whole room. I would refragment a bit to defrag it a bit. I don't know if you remember defrag. Am I too old? I don't think anybody defrags anymore. Anyway, there's a bunch of empty rows that are just taking space in the cache if I had to fetch some of you. So some of the rows are more optimized than others for that purpose. As fast as you can go through an array. It's usually pretty fast at doing iteration of component tuples. That's non-trivial to implement. But it's usually pretty good at saying, okay, give me all the items that have component A, B, and iterate to them through a zip of views, basically. Again, some system actually allows you to at compile time defines which one of the pairs you actually care about, so it can pre-generate the data in advance. Some other system will allow you to do a prepare query, where the system will behind the scene rearrange the data, so it's basically optimized for that follow-up query. You want a fast lookup of any component belonging to an entity. It doesn't need to be super fast, but for example, again, for debug purposes, if I want to say, I found an entity on the map, give me all the components and the value it has, you kind of want to be able to look that up. And finally, sometime in games, you need to have a deterministic iteration, which means if I have 2 computers playing the same game in MP, and they both iterate through all the units, I want both of them to iterate through the same order, regardless if one of them joined later in the game, and some of them have deleted and created units that the first one I've never seen. Because it doesn't matter which is alive now, what matters is that I want a consistent iteration. It's needed for MP synchronicity, usually. And finally, we want the IDs to be stable. If you create or delete an entity, the IDs of other entities should not be impacted. There's a bunch of frameworks you can find around that do that for you. Unity Engine has something which is called Burst, if I think. It's in C#, but it is an interesting case study to figure out how that works. The one that you can read out, I think, the best, because the source is the thing is open source, is Entity. It's used at least for some bits of Minecraft, as far as I know. The person who does that has an extensive series of blog posts on his blog about ECS and how you implement it. That was a goldmine to write this talk. So if you're ever interested in how you implement all this stuff, he has lots of articles about it. There's a thing called Flex. which, as far as I know, has only been used in a bunch of indie game. I could not find any big or mid-sized game studio that has ever used it, or at least they did not have a reference in their website. Sadly, it's in C, so to me it already loses a lot of points. They have a C++ wrapper, but it's C. I don't do C. And very recently, I'm told that the last release of Unreal Engine has a thing called Mass Entity. I didn't have the time to check it out, but Unreal is now trying to offer something too for Unreal games. What do we do at my company? None of this. In production, none of this as ECS. We didn't jump on the bandwagon at the time. We are looking at potentially finding practical usage in the future. Especially maybe on the engine or rendering side. So maybe having a select bits of data that are used by the game to actually be within an ECS or something similar. We keep looking at it for gameplay. We still haven't found it. And that's maybe where the thing about the ECS vibe / hype comes through. Is that I keep hearing people telling me you should use ECS, and every time I meet a peer or someone from the game industry, whatever, I say, okay, but do you use it? They're like, well, we have this bit in the engine with like 2 times that is ECS. I heard about a guy, I can't find a project that says, yeah, just about any gameplay entity in my game is managed through one ECS system. There's always a catch. So I think it's maybe because it's a framework, and being a framework, it tries to do too many things. So my suggestion is, and the way I really want you to take something away from the idea, especially if you hear about it, first be curious, look at it. Maybe it can actually work for what you're doing. But to me, what's important is not as much the framework itself, but more like what ID is trying to work upon, which is data, like providing you a way to organize your data somewhat automatically, so it's optimized for those iterations. So, yeah, you also have some problem with ID space, but I'm not going to bother with IDs right now. We don't have that much time. It's not great when your designer really likes to change the systems all the time. It's a thing that happens often in video game. Is you have a system that manages all units, and then they're like, oh, it would be really great if those 2 other systems could fit into the into this update too. Because, you know, it would be more, if everything interacts with everything, the simulation looks more like realistic to the player. That's good, but then you start having every system uses everything, which kind of beats the point of having small arrays of components of only very select data. And if you tell your designer, oh, I'm going to have to change the signature of this system to be able to access more data, it usually makes a face. It doesn't like it. So depending on how flexible you want to be, that could be a problem. So yeah, try to define your updates as free function, basically, and constrain the inputs by type. And then, okay, can we do an ECS? Can we use an ECS for this problem? Or am I good enough with a bunch of vectors? Maybe you are. I could have named this talk, I used ECS and didn't solve any of my problems, but I think that's a bit harsh on it. I think the value is to remind you that data-oriented solutions can be fast. I've made some prototyping stuff over the last year that did not use ECS, but did the idea of like, oh, maybe this system should have this internal dense array of items that are only the small bits it care about, and it could like handle maybe 10 times what another title with the same approach could handle because all the data was there. Then again, it was a prototype. Maybe once we start having designers wants to poke at it, it's going to be a problem, but at first you get really important speed-ups. Multiple component ECS implementation is tricky if you want to keep those data as like in nice ranges that you can scan in parallel. Simple component data structure is pretty simple and easy to write. There is a longer version of this talk that will be published eventually, and there will be hopefully one day an even longer version that delves a bit better on how do you want to implement that if you want to. So look at data structures that could fit the data-oriented build in your application, you know, array, vector. There's sparse dense arrays, the one that the entity uses, for example, which is basically a vector with a secondary vector that is used for lookup. That guarantees that there will be no gaps, and that even if you insert or remove, it's still like a constant operation. There is no like data moving around and everything. There's a proposal called Hive or Colony. It keeps changing names, which leaves gaps in the thing, but it tries to optimize the iteration by having like skip fields. It's not as performant, but it's also an option. I don't know if anyone still uses deck. I'm assuming for for a big enough size, it might still be okay, but I don't know. It was all the rage in the 90s. All right, so to wrap up really quickly, decouple your data, I think is maybe the main takeaway I want you to keep. I know that we really like as humans to consider like an object to contain a sum of all its properties. That has some advantages to reason about, but your CPU really will hate you when you do that because it doesn't care. It's good for multithreading, it's good for cache performance, because if you can reason about which fields are used, not only the CPU is faster, but you can reason about it, and then you can say, hey, those two fields are never read at the same time. I could put all of those on different threads, and ta-da! And finally, ECS is probably overkill. Again, I'm still trying to find first-hand feedback of someone who told me that that's the main data system they use in all of their game. But the data structures behind it are sound and interesting. So consider it the next time you have to store some stuff. Or if you have a system that's slow and you figure out, maybe we could refactor that. And furthermore, I still think your build should be destroyed. I can explain later what it means. But first, I will take some questions. The question. Who has the question? Oh, he has the question. Okay, are you going to ask me if I use an ECS?
I have a question, because from your presentation, we already know that when we fetch data into cache, whether they are in a RAM stacked or not, that hits. There is a difference in performance, right?
Yes.
But what about the second way? When we already made some operations, we have these variables in cache, and we have to write it back into RAM. Is there any difference in performance whether we have to write it in different blocks?
Yes, it gets into technical details, but there is this concept of write through versus write back. The main concept is your CPU will try to delay the writing in the background if it can and continue executing, because it doesn't matter, it has the updated value in its cache anyway. So the only moment it really needs to make sure that it's written in RAM is twofold. One, if it has to evict your data from the cache because it needs space for something else, then it has to be sure that it's been propagated somewhere else. And two, if you have several cores and they start hitting the same data, then it needs to be synchronized. There is a concept called fault sharing, where two CPUs keep writing fields that are next to each other, and they keep invalidating each other's cache because they need to synchronize on main RAM. It's really funny when it happens to you, because you realize that the more threads you have to a problem, and the more your CPU, your program slows down. You can look it up. It's called false sharing. It's when you think you're not sharing data, but you do, because you're sharing the bus, and it's a nightmare when it happens.
Okay, so it actually does matter even the other way.
Sorry?
So in conclusion, it does matter whether you store data in RAM also with writing into it back, right?
I'm sorry, I didn't catch the last bit.
Just wanted to understand if I get it correctly. So it matters also when you write back the data?
It doesn't matter as much.
Oh, okay.
Usually the CPU can do it as a background task, but there are limitations. If it is the only CPU accessing that particular bit of data, or that memory region more like, usually it's fine, you will do it in the background and you will not too often be stalled by it. You might if you start getting really way faster than your cache can write back, but it usually doesn't stall nearly as bad as when you're reading. Because also usually writing is cheaper, like you write the result of an operation that costs you something because you computed something on the CPU. So you're usually not writing as much as you're reading. If you're doing a mem copy, it's probably the worst case, I guess.
Okay, thanks.